So is my screen visible?
Yes, sir.
Okay, okay, great, great. So again, so last yesterday at night we were discussing about Bernstein Vazirani. We saw that it is a special case of Deutsch Jodza where we have fx in the form of a dot x, and we also carried out the derivation of that Bernstein Vazirani algorithm, where we saw both the cases. If the variable get z, does it takes the value of a, and what happens if it takes, and what happens if it doesn't takes. And we also saw that it is very much similar to, finding a constant and balanced oracle. So the problem of finding a binary function, whether constant balance or whether it is a equal or not equal, it remains the same. And even for Simons also, it will be something similar, where again, there will be a string. We call this like a hidden binary string or a secret string or something, you can say, as you can see in the code. And similarly, we are going to find and see like whether we can really find that string or not, using by encoding it in the oracle and doing the algorithmic steps. Okay, so this is what. And similarly, like in Simon's algorithm also, as we will see now after this, and this is very short, but in Vazirani, very straightforward. So in Simon's also, again, the problem is similar. Again, you have two binary process, uh, one function will be like 1 to 1, another one will be 2 to 1. You have to find whether it is 2 to 1 or 1 to 1. So very, very similar. Okay, all these algorithms, Deutsch, Jodsa, Bernstein, Vazirani, Simons, these are one of those earliest quantum algorithms showing advantage, and they are very, very similar in flavor. So if you learn one of them, the other ones should be easily understandable. Again, you do not have to memorize all the derivations, etc., which you are writing. Okay, memorizing will not give you much. Just understand it, like what is happening in the algorithm, what are the steps. That's it. No need to memorize anything. Okay, understanding is more important. So let us see. So again, this is Qiskit. So by this time, you are all familiar with Qiskit. We have last week discussed Deutsch Jodza code as well, and many things going on, right? And you are also practicing for Qiskit, and maybe some of you will also give the IBM Qiskit developer exam as well. I highly recommend that you give that. It's a nice way to, revise all the concepts on Qiskit. If you require separate training on that exam, I have given several trainings before for that exam, and people have cleared it in first attempt. So I will be also happy to give some training to you later, not now, but maybe after this course ends in December, because the advanced course will start in November, and we are planning to finish it by December second week. Okay, so maybe after that, if you like that, okay, I want to do this training also for exam and want to give the exam, then we can decide some time slot and do that also. Okay, now again, like as I said, again we have number of qubits. So as we took an example yesterday, right? We took a as 0 1, z as 0 0. We saw that, okay, they are different, and because they are different, therefore the amplitude goes to 0, etc. We have analyzed that situation using quantum circuit analysis, measurement, everything. So similarly here, the c which you see, the hidden binary string, that is your basically a. Okay, the variable is changed, but anyways, you can name it a as well. That doesn't matter. So and then the number of qubits used to represent will be 3, right? So therefore, the first register qubits will be 3. Okay, and then again, the steps, and these are very similar to what you have actually done. Okay, in the Deutsch Jodza. So for example, you created that quantum circuit, then you put the ancilla means the last qubit, basically ancilla state in the K to minus. Okay, and then once you do that, then what you do is that you apply Hadamard gates before querying the oracle. This we already know, right? We have to apply Hadamard gates to the first register qubits. Then we make a barrier and then we apply the oracle. Okay, so for the oracle, whenever we have a, 0, we apply identity. Whenever we have a 1, then we apply the C naught gate with the control as that qubit, which is 1, and the target as the, again, the last qubit, second register. Very similar to Deutsch Jozsa. Okay, just connect it with Deutsch Jozsa, and you should be able to find that this is very similar to that. Then again, you apply Hadamard to the first qubit and you do a measurement, and that's it. So this is the case. So we took 0 1 1, right? I mean, if you remember 1 1 0, we took 1 1 0. Okay, but we reversed it according to Qiskit, right? Here we reversed it. So reverse C to fit Qiskit's qubit ordering. So it became 0 1 1. Okay. So basically, if you see that 0 1 1, then here it is 1, here it is 1. Okay. 0 1 1 we are considering. Okay. Here we are not wrapping. Okay. Like Deutsch Jozsa, but very similar. We have the C knots. Okay. And these C knots are then actually what they are doing, they are having the control as that one qubit, which is like 0 1 1. So wherever there is 0, identity is applied, and then 1 1. 1 is the second q1, and then q2 is also 1. So therefore both has the controls, and the target goes to the last second register qubit, which is always a single qubit, if you recall from your Deutsch Jozsa notes. Okay, so that's why the notes taking is very important. Like while I am teaching you, immediately try to write down quickly all the notes, because I will keep on referring back to them. So then that is important for your remembrance also. Like what we have studied in the past, how I am connecting that with the present study. This is what you should also do for any subject. As I said you yesterday, you should do this for any subject, not only quantum computing, but any subject which you're studying in your semester. You should do your best to connect it with the previous concepts. In that way, you remember both of the stuff easily, the current also and the previous also. Okay, and then you will, this code is the same. Okay, I'm not going to explain this again and again. Okay, this is the same code. Okay, and then what you see is that the result, okay, the resultant string. So we can see that the result of measurement is the hidden string. So therefore Z is indeed able to take the value of A. Here A is C. Okay, so you can say Z is equal to C. Okay, so for Z is equal to C, the amplitude is higher, and we are able to measure the string which we have with full possibility. Therefore the algorithm indeed, it indeed works. Okay, so that is it. I mean, Bernstein, we don't have much actually. Only this is the part. So this is how we are trying to find. So we are getting 1 1 0. We are getting the, like, same result. Not getting it reversed because we already reversed it in between. So to fit Qiskit's ordering. If you do not reverse it, then you will get, like, 0 1 1. Basically, you will get the other. But I mean, that's also fine because you already know that Qiskit has a little Endian ordering system, right? So even that is also fine. But yeah, this is just for convenience. Okay, so just I will be sharing these notebooks again. Okay, now I think from now onwards, like, everything will be on the VIT Club GitHub link. So all the days of notes and everything will be uploaded to the GitHub, and everyone will have the access link, and you can check it from there itself. Okay, now let us let us go ahead with the Simon's algorithm. Okay, let us study Simon's algorithm. Again, by knowing Bernstein, Simon's algorithm path is much clear now. So you should be able to understand it. That is also will be some, like, finding some hidden bit string. So let us take, and you will see that all these applications are very simple. So that was indeed the case in the beginning. When quantum started, we started with some simple concepts, right? I mean, whenever we have a new technology invention or something, we first start with some simple problems, whether the new technology can solve our simple problems or not, right? And since this is a computing, that means computational technology, therefore we started to see that whether it can find the answers to simple problems or not. That's why you will see this hidden bit string, like simple problems, then finding balanced oracle, etc. They don't have too much meaning in today's real life. We don't do them, we really do not use these four algorithms, okay. But the main thing here to understand is it's not about the usage, but to understand the motivation of how the field is emerging, how it is growing. So let us see. So let us we will see the Simons. Okay. So okay, Simon's algorithm. So let us see. So Simon's algorithm was the first quantum algorithm to show an exponential speed up versus the best classical algorithm in solving a specific problem. Okay, what it is saying, Simon's algorithm was the first quantum algorithm to show an exponential speed up versus the best class. So again, the same thing. This is also similar to, like, Deutsch we are seeing, like showing the speed up, okay, showing the value of quantum properties like superposition, interference, etc. Okay, basically it is that we already showed the value of entanglement, right? We have already seen. You have already studied what is teleportation, quantum teleportation, and super dense coding. You saw, right? That is the value of entanglement, right? A very very important uh, tool in quantum communication, cryptography. Okay, these kinds of subjects. Okay, sensors, etc. Okay, so you have already seen the power of entanglement, and we will keep on seeing that, of course. But these algorithms demonstrate you more properties, okay, of quantum superposition and interference. Okay, so I've already explained quantum interferences were happening in Deutsch and Bernstein Vazirani is a special case of Deutsch. So therefore, definitely there also quantum interference is there, and similarly in this one also. Okay, now both Simon and Shor's algorithm are well known prime factorization algorithm solving a similar problem. Okay, solving a similar problem. So basically, like, as I have mentioned you, I think sometime I have mentioned you before that Simons has some similarity with Shor's on finding the period of that function. Okay, given a function given a function f, find the period of that function. Okay, finding the period of that function. Okay, but this is also used for, this is also, but also, and we are going to see this also for period finding. We will leave it for Shor's algorithm, not with the Simon's algorithm. Also for finding hidden bit string, which we have seen just now with Bernstein Vazirani. So the concept is clear to you what we are going to do actually. So let us start with the Simon's problem now. Okay. So what is Simon's problem statement? As we have seen for, like, every algorithm, right? Dude Joza. Then yesterday we saw for Bernstein Vazirani. Okay, problem statement. So similarly, Simon also has a problem statement, right? Finding one to one or two to one. Those two, which I was saying you just now. So Simon's problem given, okay, given an unknown, given an unknown function f, where again we are defining f, it goes from 0 to 1n and gives an output 0 to 1n. Okay, which can be which can be what, which can be first case 1 to 1. Okay, which can be what, 1 to 1, which is maps exactly one unique output for every input. Okay, so what does 1 to 1 does? Maps exactly one unique output for every input. Example, f of 1 is 1 and f of 2 is 2. This is just an example. Okay, maps exactly one unique output for every input. Okay, what does that mean? Maps exactly one unique output for, it's very self-explanatory. That means whatever you have the input and exactly you will get that a particular output for that. So f of 1 is equal to 1, f of 2 is equal to 2. Similarly, f of 3 is equal to 3 and f of 4 is equal to 4. Okay, so here in this case, algorithm output will be, so let us see what will be the algorithm output, all 0 bit string only. Okay, so therefore when we see that there is a all 0 bit string, therefore the function is 1 to 1. Okay, very similar to, like, in Deutsch Georgia, if you remember, we were seeing all 0 and not all 0 bit strings. Not all 0 means it was balanced, and all 0 bit string was constant, right? So here also very similar. Look, like all these algorithms, how they are so similar. So this is how, when they're similar, so you should be able to connect with the past concepts, and like looking back at your notes again and again. That is what I would always say, look back at your previous notes, If you have not written them, please do write them today itself. Please do write them, because sometimes we see, like, if we keep getting delayed, then it gets delayed, right? Then we get caught up with other works. So it's better that, like, you write it today itself. If you have left anything, that will be better. It will be very helpful. Then 2 to 1. 2 to 1 will be maps exactly two inputs to every unique output. Therefore, what it means is that, let us see example. So, like, f of 1 will go to 1, f of 2 will go to 2, f of 3 will go to 1. So, two inputs. Okay. And f of 4 goes to 2. So, as you can see, for 1 and 3, the output we are getting is 1 1. And for 2 and 4, we are getting, for the inputs 2 and 4, we are getting 2 2. Okay, so therefore two inputs map to a unique output. And therefore, in this case, algorithm output is, whenever it is like that, it is our hidden bit string. Okay, so basically our hidden bit string belongs to the 2 to 1, and this algorithm will try to find whether it is a 1 to 1 or a 2 to 2 to 1 function. Okay, so therefore this, now let us see. So this 2 to 1, 2 to 1 mapping is according to a hidden bit string, right? It is according to a hidden bit string. So hidden bit string, let's give it a name. Let's say it is some bit string S. Okay, we have seen like this hidden bit string process in Bernstein just now. So, and then, but then according to that, so given, like, what is the formulation? Given x1 x2, we have f of x1 is equal to f of x2 if x1 is equal to x2, or it is guaranteed that x1 XORed with x2 is equal to s, or x1 is equal to x2 XORed with s. So basically x1 x2 are your inputs. So we are checking if, like, the inputs are equal or what the inputs can be. Okay, so x1 XORed with x2 is equal to s. That means, like, that is the calculation which is done in based on the inputs which we provide to the algorithm. That kind of calculation is done inside the quantum algorithm, and once that is done, therefore we try to analyze that whether, like, indeed the XOR output comes out to be s or not. Okay, so that's the internal. This is like the, like, this is very similar to what we see in Deutsch algorithm. If you remember, there also we were taking f0 XORed with f1 is equal to 0 or not, or f0 XORed with f1. Okay, so we were taking both the input 0 and 1. So here also, like, we are taking x1 x2, a generic input basically. So if s is equal to all 0 0, okay, it represents 1 to 1 f. Okay, one-to-one f means one-to-one function. Okay, so if s is, so it's decided directly. Okay, if s is equal to all these zeros, it represents one-to-one. But if it is not, then definitely it is two-to-one. Okay, so that is how we can detect. Now let us see a few points. So what we have is that the best classical algorithms, including probabilistic, ones, require an exponential, okay, 2 to the n by 2 queries to the black box. So here also we have a oracle, right, which encodes the function. So we call black box function, as we saw in Deutsch algorithm first time, in order to. So basically it is saying, like, we are again comparing it with the classical case, as you have already done this before. So just not explaining it too much, but I mean, this is a understood thing, and you have also seen it for Tuch, Jones, etc. That how we are comparing it, and how the classical takes how much number of complexity, and how quantum does it in one query, etc. Those things we are basically comparing. Okay, so you're already familiar with this. If you have again, like, taken the notes, then you definitely know what this is about. Okay, and again, please note down the notes today itself, like complete all the previous week's notes and today's notes also. I have already sent the previous week's notes, so it should not be difficult. And Simon's algorithm, what it will do. So classical algorithm was taking omega 2 to the n by 2 queries, okay, to solve this black box function to determine the hidden string, let's say. And Simon's algorithm solves this problem in polynomial time. Okay, it solves this problem in polynomial time rather than in exponential time. Okay, performing an optimal O n queries. Okay, performing an optimal O n. So that is the basically complexity of Simon's algorithm. You can say that it is able to give you the result in polynomial time rather than taking exponential time, which classical algorithm or probabilistic ones take. It is able to give you in polynomial time, performing an optimal. This is the optimal value O n queries. Then one last point, and then we will move to the circuit derivation. So Cyber's algorithm requires some processing at the end, solving a system of so okay. So this is for the this step is for the period finding. So Cyber's algorithm requires some processing at the end. Okay, just a moment. Somebody is joining. Let me see. Okay, Cyber's algorithm requires some processing at the end, solving a system of linear equations in order to what? In order to determine the final solution. Okay. So basically, I mean, this step is for, like, the period finding. We are not going to solve solve this, but yes, it is there for period finding. We are only going to do for the a simple application for the hidden bit string search. Now let us move on to the circuit by giving the relation, like, the formula for Simon's oracle, just as we did a formula for Deutsch's algorithm, if you remember, like x y and then given x comma y XOR fx. Do you remember that, Deutsch? If you do not remember, please take a look at your notes. You will find that formula x comma y. We are using that in step 2. Okay, I remember. So maybe you also remember. Just have a look at your notes now itself, and you will see that we are using in the step 2 x comma y ket x comma y is equal to ket x comma y XOR fx, right? We were using that formula. So similarly here also we have the Simon's oracle formula. So Simon's oracle implements the unitary operation. Okay, it implements the unitary operation. So what is that unitary operation? UF. Again, it's the same thing in Deutsch algorithm, which is equal to x y XOR fx, but in Simon's we have y is equal to 0. Okay, it is not it is basically, it doesn't starts with 1. So y is equal to 0. If y is equal to 0, then the formula we get u of f applied to get x. Okay, this is get x, remember, this is get x, and then get 0 is equal to x y XOR with 0 XOR with f of x. Okay, you will get f of x back. Okay, so this is the primary formula for the Simon's oracle. Okay, just a little bit of modification. We start with all zeros. Now the second qubit is also starting in 0. Okay, now let us we can only, with this information now we easily start doing analysis. So Simon's algorithm quantum circuit analysis. Okay, we are going to do Simon's algorithm quantum circuit analysis, right? So let us see a few steps of this, and maybe we can stop and continue in the evening. Till that time, just go through the all the algorithms which we have done till now. And I will also be sharing soon the yesterday's video recording, yesterday's class also. Okay, this recording is currently in progress, so this cannot be shared because Google also takes its 1 or 2 hours of processing time. Sometimes it takes more than 2 hours as well, so for longer videos. So but the yesterday's video is already processed, and that will be shared with everyone very very soon. Okay, now let us see. So let us start with the circuit, as we have already done this, so this should not be so difficult for you to understand. We have done this several times before now. So let us again, we have started with gate 0, and then we apply Hadamard tensor n, and like this. Then we are starting with ket 0, as I told you, and you also saw in the formula y is equal to 0. So we start like that, and then apply the we apply the oracle u of f, okay, where you can already take the measurement of the, this is a bit different, okay, it's a bit different. You can already take the measurement of second qubit and make it collapse, okay. um, but you will again apply the Hadamard, okay, and the measurement, okay. So very like, I mean, you will observe this is very similar, okay, isn't it? This is very similar to what you have done, but the only thing is that now you are applying another measurement in the second qubit to make it collapse, okay. And this is where your XOR functionality and all those stuff is coming into the picture, okay. So we are going to see that in step 4, basically step 4, okay. So let us do till step 4, and then we in the evening we can continue from step 5, see the Qiskit version of Simon's algorithm, and this algorithm will be finished. Okay. So let us do like that. That's a good plan. So let us see now. Again, I'm drawing the dots. So start noting them down. Okay, one. This is one. This is two. Okay, this is three, four, five, six. Okay, we have some extra steps due to the measurement which we have on the second qubit. Okay, let us begin. Let us start with step 1. You already know how it is done. So let me start writing, and it is very straightforward. So again, step 1 will be to n qubit input registers are initialized to the 0 state. So ket phi 1 is equal to ket 0 tensor n and ket 0 tensor n. So basically both the register. So both the register here. So this is the first register. Okay, this is the first register which can be of n qubits. Okay, and this is the second register, and this can also be of n qubits. Okay, so this time it is not a single qubit, as you can see. It can be of n qubits. Okay, so a bit more generalized, you can say, than Deutsch-Jodza, because in Deutsch-Jodza you were not having the second register as multiple qubits. If you remember, just take a look at your notes again. In Deutsch-Jodza you are not having the second register as multiple qubits. In the second register you only have a single qubit. Only the first register has multiple qubits, right? But here both of them can have n qubits. Okay, now step 2, apply Hadamard. Okay, apply Hadamard gate to the first register. Okay, apply Hadamard gate to the first register. So get phi 2, basically. Okay, so again I'm just using the same formula. So I mean, you all are aware about this now. You have used it several times. So I'm not going to explain them. Okay, you are already aware about this, what this is, and zero is also there. Okay, and now what will happen? It's step three is that we will apply the oracle. Okay, so let us apply the oracle. So step three is apply the oracle. Okay, oracle function uf. Okay, get phi 3, right? Get phi 3. Okay, to the n summation x belonging to this 0 1 and get x and basically f of x. Okay, so applying the oracle means, like, this is that formula, get x comma f of x. We saw that formula, right, just now. If y is equal to 0, you have written it down, right? Just check, like, you have written it down. Simon's oracle implements the unitary operation, this line, uf get x get y is get x, like I gave you the example of Deutsch algorithm, and then we put the y as 0, right? And then we saw that uf of get x get 0 is x comma f of x. So it's the same thing. That is a formula which we applied. Okay, so just now we wrote this. Okay, we are just applying it here in step 3. Okay, nothing new. And then what will be step 4? So till this point let us stop. Okay, let us do till step 4, and then next of the algorithm will be remaining, a little bit will be remaining, and then we are also going to see the Qiskit version in the evening. So now what will happen, and this is the important step. Okay, so please observe carefully. Now we are going to do measure the second register. Okay, what we are going to do, we are going to measure the second register. Okay, now remember one thing. Remember, in the like, as we were discussing about 2 to 1 mapping, we were seeing a special structure of this hidden bit string or the secret string, whatever you want to call it. You can call, we were seeing a special structure for the string. What was the structure? X1 XORed with x2 is equal to s, right? We have seen that, right? When we were discussing Simon's problem just now, we have discussed Simon's problem. Okay, and 2 to 1 mapping, there we saw that 2 to 1 according to a hidden bit string s. Okay, where it is guaranteed that x1 XOR x2 is equal to s, or x1 is equal to x2 XORed with s, right? That is what we saw, right? So basically, that is the condition which actually comes into the picture here in the step 4. Okay, so because of that setting of the problem, okay, this is how we set the problem. Because of setting of the problem, the what is the concept primarily used? Okay, so let us see what is the concept primarily used is that. And if you do not understand this step fully, you do not have to worry. Just remember that formalism, x1 XORed with x2 is equal to s, that one is enough. Okay, f is z2 to the n periodic. Okay, z is what? Z is a integer, right? We have, like, as we have, we denote the natural numbers, whole numbers. Okay, we denote integers by z, right? Then we denote real numbers by r, and complex numbers by c, right? I mean, these are those symbols which we use in mathematics, right, to denote all these spaces. So basically, what is the concept that is primarily used behind that x1 XORed with x2? Okay, the just giving a brief intro to that. Okay, this has other mathematics as well, which goes into abstract maths. So we are not going to go into abstract maths right now. Okay, I'm just going to give you a small glimpse. If you do not understand these steps, do not worry too much. Okay, so where it is used that f is z2n periodic with an unknown period. That period is s. Okay, so if the function, okay, which we are trying to find out, that function is z integer 2 to the power n integer periodic, that means binary integer periodic. Okay, binary 2 to the n is what? It is binary, right? Not decimal. 10 decimal is 10, 10 to the n, right? Not decimal, but binary periodic. Okay, z binary integer periodic with an unknown period s. Okay, so therefore, and again, like, you can represent it's like a z, double z. Okay, double line z. Okay, can implement it like that. Z 2 to the n periodicity. What it tells you? Okay, what it tells that the domain of this periodicity. Okay, z2 to the n periodicity, the domain, we have domain codomain, right? We have domain codomain in relations and functions, you have studied, right? So basically that domain we are talking about, which you have learned in school in relations and function. Okay, so that domain can be partitioned into two disjoint sets. Okay, that domain can be, and again, if you do not understand, you do not need to, like, frustrate on this too much. Okay, this is just a glimpse of the where the concept is coming for this hidden bit string, etc. Like the concept which we have written, x1 XOR x2 is equal to s, that rule. Okay, that thing, where it comes from. Okay, so this is for that, can be partitioned into two disjoint sets R and Q. Okay, it can be divided into, like, R is real and Q is rational, right? You already know this, right, from school life. R is real and Q is what? Q is rational. So therefore you can divide it. Okay, Z2 to the n periodicity is R union with Q, where R takes these values of x. Okay, x, this is x, let's say it takes values of x, and let's say q is taking values like this, x XORed with 0. So therefore from that, q can be written as q is equal to r XORed with s. Okay, with the period, if you remember, s is the period here. Okay, but s is also our hidden bit string. Okay, but for this step, okay, we are considering that as a matter from a mathematical viewpoint. Okay, we are not considering it a hidden bit string or something. We are considering that it has some unknown period, because this function is z2 to the n binary integer periodic, and it has some period s. Okay, so therefore r XORed with s, which is a what? Which is a coset of the set R. So we have already seen that disjoint sets R and Q, and where we see that this Q is the coset of set R. Also, R is equal to R XORed with 0. We can also write it like that. So we get two cosets. Okay, it's like two complementary. Okay, coset is like more like a complementary set. Okay, because you can see that Q is equal to R XORed with S. Okay, so something like, complementary with R, just as we have complementary angles, right? One is theta, one is 90 minus theta, and like that. So something similar kind of like that situation is happening here, where we have Z2 to the n periodicity, and you are able to write it in the format of R union Q, where each of them takes form of X union with X XOR 0, etc. And then you are able to see that Q can be written in the complementary format R XOR with the periodicity of that Z2 to the n, which is S, and therefore that is a complementary set of set R. And also R itself can be written with R XOR with 0. Now anything XOR with 0 is the value itself, right? We have already seen that 0 XOR with fx was fx. So similarly R can be written like R is equal to R XOR with 0. So therefore we get two cosets, so two complementary sets. What are those? R and Q is equal to R XOR with S. Okay, so therefore these are the two cosets we get, complementary sets. Okay, now what will happen? Now let's consider an element X, okay, which belongs to one of this coset R, has a unique partition. Since they are complementary, remember, R and Q are complementary, so therefore element X belonging to R has a unique partition in Q. Okay, which satisfies what? Which satisfying, what is the relation they're satisfying? One is X and one is X XORed with S. Remember, R Q is equal to R XOR with S, right? And this time X is belonging to R, right? Okay, X belongs to R here. Okay, and Q is what? R XORed with S, right? So therefore we replace that R with X element, because we are taking an example of X as the element, and therefore X XOR S. With these two conditions, we have the function. So of course X belongs to R here. This is the function f of X, and therefore with this in mind, therefore value of f of X could correspond to X and Y is equal to, so where Y is equal to X XOR S. Okay, now can you see something? X XOR X, x1 is equal to x2, or x1 is equal to XOR S. If you remember that condition, x1 is equal to x2 XOR S. Can you remember that? And Y is equal to X XOR S. So therefore Y is x1. Compare this. Okay, how we are deriving this condition. Look at this very carefully. That's why this step is important, right? Why this step is important? Look at how we are deriving that condition, 2 to 1 condition, which I have told you in Simon's problem. Look at the section which you have written in your notes. What is written there? X1 XORed with x2 is equal to S, and x1 is equal to x2 XORed with S, and we are deriving that same thing. One is X, and therefore another one, x1 is equal to x2 XORed with S. That means Y is equal to X XORed with S. Only the variables are changed. Okay, but the concept is similar, right? So this is what you should be noticing. Okay, how we actually are getting to that condition by taking this help of the complementary sets. Okay, then we take an element from that, okay, two elements, and then we are able to define the function from itself, which is a 2 to 1 function. Okay, so this is like more like a derivation step for that 2 to 1 condition. Okay, x1 XORed with x2 S, or in other words, x1 is equal to x2 XORed with S. Okay, so and therefore, and the first register, therefore the first register value will be, the first register is collapse 2, because we have taken measurement, right? Remember, we have taken measurement. So therefore ket phi 4 is equal to 1 by under root 2 ket x plus get y, a superposition state of get x plus get y. This is what the state is at after taking the measurement, because remember the second register has collapsed, therefore it has vanished. You do not need to write. This is only the first register case, right? Only the first register case. Therefore, this is the step. Okay, step 4, and very important step. Even if you do not understand, okay, do not worry too much about it. With the time, you will understand. And again, it's not very necessary. Just remember that condition which we have discussed before. This step is more like a small derivation of that condition. Okay, in much more easier terms. Okay, which involves some, like, amount of abstract algebra and some number theory, etc. Okay, we are not going to go into that. I am also not a mathematician who knows all the abstract algebra or who knows all the number theory. Okay, so therefore not going to too much deep into that, but just to expose you to the concepts, what the concept is involved for the derivation of the 2 to 1 mapping process. Okay, that's what my goal is. Okay, so let us continue in the evening. Let us stop here. Okay, already this lecture has become heavy with step 4, right? I mean, step 4 itself is a, like, very heavy part. As you can see, this is one of the, like, itself is a conceptual part in this. Okay, so let us stop here, and then let us meet in the evening again, 7 to 9. So that's the maximum time, right? 2 hours. But yeah, again, it won't take 2 hours. I think it should take only about an hour or maybe less, because we will then finish the analysis of Simon's algorithm, and we are going to see the derivation of the Simon's we are no, not derivation, sorry, we are going to see the Qiskit version of Simon's algorithm. And then yeah, whatever the next topics are coming, then they will be taught. Okay, so let us stop here. So have you all, okay, yes, another thing, have you all written the notes?
Yes, sir.
Okay, okay, great. Great to know this, Aditya. This is very good. So go through the notes again, which you have written, and consider checking them, consider connecting them with the previous stuff which we studied.
Got it, sir.
Yeah, okay. So, okay, then I am stopping the recording. So let me stop.